So let us start with the third unit, that is columns and struts. Now, this is relatively the most one of the most easier units. So, unit 3 will be easy as compared to all other units, and if you put special focus and prepare yourself such that you don't miss out on any questions on unit 3, and one more unit is unit 4, half of the portion, that is thin cylinders. They are relatively easy, means they are formula based or the derivations are not that so typical, and probably they do not require a lot of understanding. Then these are the units, means you can place special emphasis on them, and they fetch you marks. The rest all you need to understand, you need to be very concentrated, and if the basics are not cleared, it becomes difficult for you, because formula based problems don't restrict yourself to university syllabus. And in university also you have a number of problems which are not exactly related to a formula. You need to understand why this formula has been specifically used. So starting with columns and struts, you must have seen a beam like this. This is a beam, and it is being supported. Let it be on any type of support. When you have a load, this beam deflects by a certain amount. So this amount is called as deflection, and you can find out slope at vary. Now beam is a horizontal member which is carrying a certain type of load. Now you have a vertical member. Now vertical members, let us say, uh, this is a column, and on a column, the most common example that you can see is in civil constructions. You, in everybody of your house, you must be having columns and beams. A beam is a horizontal member which supports the vertical load, and you have columns which support the beam. So the beam is supported here on the column, and if you see this is a column, again this is a column, and it has been this is supporting a beam. Obviously, this is a fixed beam. It is supported from all three ends here and all three ends here. It will be having six reactions, but let us not go into reaction. Now, these two are columns. Now, these two columns are acted upon by axial compressive loads only. They are acted upon by axial compressive loads only. The most common material that is used to create these columns are RCC. So RCC is reinforced cement concrete. RCC is reinforced cement concrete. Now the composition is cement, sand, chips, water, and steel. Now, if you look at all these things, water is used as a binder to join these three, and you have steel as another member. The If you look at the purpose why steel has been inserted, let us see this cement. Now, cement has an advantage that it has immense compressive strength. It has immense compressive strength. And the disadvantage is poor tensile strength. So, this is a very good advantage. I mean, cement is one such material which has excellent, or you can say the best possible compressive strength. And disadvantage is it is the cheapest material to have the best possible. And the disadvantage is it has a very poor tensile strength. This is the reason why, if you look at advertisements like certain advertisements that you see on TV, we say Virat compressive strength. So, Virat compressive strength means it has excellent compressive strength properties. And in columns, it is acted upon by axial compressive loads only. So, this is relevant enough or sufficient enough to handle any type of loading. Now, the situation arises when why is steel used? Steel is used when, in spite of compressive loading, in spite of compressive loading, if tensile stresses are produced. Now, tensile stresses means resultant stresses. Tensile resultant stresses are produced to counteract or to look into that situations. Steel is used because steel has excellent properties in compression and tension. The, the reason why steel has been used is we know that we will be only encountering compressive stresses, and cement is sufficient enough to handle those stresses. But there are situations where, in spite of compressive loading, the resultant is a tensile stress. In those situations, we use steel. We use steel so as to encounter those situations, because those situations they will arise. So if they arise, then steel will be taking care, because it adds or supplements to the compressive properties of the cement, and it is capable enough to handle the tensile component of stresses if at all they occur. Now, let us, what we had seen earlier was, if you have a shaft which has been supported at two ends by two bearings, and you have a flywheel or another bearing posted at the middle, then what happens? This becomes a beam, and it is subjected to combined bending and torsion. Now let us come to another situation. In columns, what happens? Suppose this is a column and this is your neutral axis. So let us say that it is acted upon by a load here, P. So stresses is equal to uh, force upon area. So you can calculate and these stresses will be compressive in nature depending upon the type of loading and the direction of loading. Now, if you have the same column like this, and this is your centroidal axis, and now it is acted upon by a load here at some eccentricity E. At some eccentricity E. So this eccentricity will lead to the production of moment. So this becomes a case of combined direct and bending stresses. As both these stresses act along the same axis of the shaft, they are directly added. So the direct component will be equal to uh, P upon A, and the bending component is given by My by I. So what is M here? M is P into E, eccentricity from the neutral axis. So P into E becomes M, and this is Y divided by I. So the resultant stresses, this is given by P by A plus minus Pey by I. So this is the statement for combined direct and bending stresses. Now here in this problem, if you see, the load is positive and it is compressive. In this statement, the load is positive. We have represented the load everywhere as positive, and the and it is compressive in nature. So that means in this statement or in this equations, compressive denotes positive stresses. If sigma r comes out to be negative, that is, it is now tensile. So in spite of applying a compressive stresses or a compressive load onto the bearing, onto the column, the resultant, if it comes out to be negative, it means that it is tensile in nature. So you can say that sigma r should be greater than equal to 0. In all cases, sigma r should be greater than equal to 0. So this situation has to be followed. So uh, this is the equation, or this is the understanding for combined direct and bending stresses. So this is for combined direct and bending stresses. So you need to understand why this cannot be negative, because negative here will now lead to production of tensile stresses, which is not required because the material that has been used to create the column is good in compression only. So this is the basic understanding of combined direct and bending stresses. So now if you look at the sigma resultant, this is equal to P by A plus minus Pey by I. So sigma max, this is equal to P by A plus Pey by I. Now max means this is compressive in nature, compressive is positive. So this you need to remember. Compressive is positive because the load that is acting on the column will always be compressive in nature. There is no possibility that you'll have a tensile load acting on the column. So this is the reason why compressive has been intentionally taken as positive. So if you come to sigma minimum, this is P by A minus PEY by I. Now, in all cases, sigma minimum should be greater than equal to 0. ठीक है? If this is done, then this is okay. If sigma min comes out to be less than equal to 0, that means tensile stresses are produced. Okay, you must also, means I was expecting that some of you, or at least one of you, may have asked why this is plus minus. Now, plus minus means this situation has come because if you see a column here, this is your centroidal axis. This is P here, this is P here. If this P is on the right hand side of the centroidal axis, it will produce a clockwise moment. Clockwise moments are positive, so they have been represented. If it is to the left of it with respect to the centroidal axis or the neutral axis, it will produce an anti-clockwise moment. So anti-clockwise moment will be represented with a negative sign. This is the reason why it is shown as plus minus PEY by I, because E eccentricity can be on both sides of the column or both sides of the centroidal axis, not only to one side. It is not restricted to only one side. It can act on any side of the centroidal axis. So मैं बार बार आपसे पूछ रहा था, I was expecting that some of you may at least ask कि ये plus minus कहाँ से, either it will be plus or minus, how can it be both? But still doesn't matter, it indicates how seriously you are listening to it. So if you look into this, if you look at types of columns, or if you look at cross section of columns, they are of two types. One is a rectangular column. आप घर बंगले महल किले सब में देख लो, you are having two types of columns. One is a rectangular and the other one is circular. These are two types of two cross sections. A rectangular obviously means that it can be a square also. Okay, so square is a rectangle of both sides equal. So a rectangular, it can be a rectangular or a circular. You will never find triangular or any other type of or any other cross section of columns being created. So they are only of two types, rectangular and circular. So let us take one column at a time. Okay, what are the conditions that in spite of compressive load, uh, a tensile stresses can be produced? So the first, let us start with a rectangular one, rectangular column. If you have a rectangular column, then if you look at this equation, sigma min, if you take P by A common, this is 1 minus, let us not take common as of now. We have a rectangular column and let us solve for it. So sigma min is equal to P by A minus P E y is how much? B by 2, because when it was a horizontal one, it was Ixx. Now it is Iyy. It is a vertical one. So this becomes Ixx gets replaced by Iyy. In horizontal columns, it is Ixx. In vertical columns, it is Iyy. So this is Pey divided by I. I is dV cube by 12. Okay, so if you put down here, you have sigma minimum is equal to P by A minus 1B, 1B, they get cancelled. So you have 6E P into 6E divided by, this is dB square. So dB square, let me write down this as B into D into B. Now B into D is your area. So that means if I take P by A common, it is 1 minus 6E by B. So for, in this situation, sigma min has to be greater than equal to 0. So P by A will always be greater than equal to 0. So 1 minus 6E by B should be greater than equal to 0. So, or you can write down 1 should be greater than equal to 6E by B, or you can write down B should be greater than equal to, sorry, or E should be less than equal to B by 6. Okay, आप इधर ले जाओ, reverse the signs. E should be less than equal to B by 6. So eccentricity at which the load should be applied should not exceed B by 6 along the width of the column. Okay, so from this derivation, we have seen that E should be some magnitude, or E should be some value which is less than equal to B by 6. So if you look at the column, suppose this is the column of a rectangular section, and this is your centroidal axis. Then this distance should be B by some value less than B by 6, and this distance should also be some value less than B by 6. So the total range in which eccentricity can vary is B by 6 plus B by 6. So this is equal to B by 3. Therefore, it is called as middle third rule. You have this B by 3 term. This eccentricity can vary from B by 6 on one side to B by 6 on the other side. If you add them, the total range in which this variation can take place is B by 3. Therefore, it is called as middle third rule. Now, this is about middle third rule. Now, the next type of cross section, which is quite used or most commonly used, is a circular cross section. So if you have a circular cross section, again sigma min should be equal to P by A minus PEY by I. Let us put down the values. Sigma min is equal to P by A, let it be A. This is minus PEY, this is P into E into Y is D by 2, and I is pi by 64 D to the power 4. So from here you have P by A minus P into E into 16, sorry, not, this is not 16, to 32 by pi d cube. Okay, so if you want to write this in area form, This is P by A minus PE into 8 divided by pi by 4 d square into d. Now P by pi by 4 d square becomes your area again. So you can take P by A common. So this gives you 1 minus 8E by d. Okay. So for compressive stresses only, so it should be 0 should be greater than equal to P by A. Obviously this term has to be some value greater than 0. So P by A 1 minus 8E by D. So again P by A will always be a value greater than 0. It will always be value. So this term has to be greater than equal to 0 because this cannot be negative. If this turns out to be negative, the entire term will be negative. So you can write this as 1 minus 8E by D has to be greater than equal to 0. So E has to be less than equal to D by 8. Now D by 8 means if this is your centroidal axis, then this two distances, this cannot exceed d by 8 and this cannot exceed d by 8. So the range of application of load is d by 8 plus d by 8. So this comes out to be d by 4. And hence this is called as middle quarter rule. So this is middle quarter rule, which is applicable for circular cross sections, and the previous one we studied was middle third rule, which is applicable for rectangular sections. The purpose of telling you about these rules are these rules help us to understand that in spite of application, they help us to understand the conditions under which, in spite of application of compressive loads, it may lead to the production of tensile stresses. Okay.